Hello students, in this video we'll see an example of finding a conformal mapping which maps a region between two circles to a region onto a strictly speaking annulus centered at the origin. This is called circle centering, is a very classic problem in conformal mapping. So let's consider the following region. Consider the region. I'm going to draw it because it's easier to see if we draw it. Here's the x-axis, here's the y-axis, and then here's the unit circle. That's the unit circle. That's x squared plus y squared equals 1. Okay. And then I'm going to draw another circle over here. So it's not quite centered as we can see from this. I'm going to call this point over here B. I'm going to call this point over here A. I'm going to assume that A and B are real numbers. And so what I have is I have the region between these two circles. So it sort of looks like an annulus, right? Except now the circle's not quite centered, right? So it's not centered. I want to figure out how I can take that circle and center it, okay? So the region between the unit circle and the circle traversing the points A0, B0, and the origin, right? That's of course the diameter. With what? With A, modulus of A, of course it's negative in this case, modulus of A less than B. Okay, excellent. Now, can we map this onto an annulus centered at the origin? Okay. And so to do this, we want to recall a very nice collection of functions, right? Let's recall we have our Blaschke factors, our conformal automorphisms. We have single Blaschke factors. Or the conformal automorphisms. Conformal is a key there. Conformal automorphisms of the unit disk, right? So what are these single Blaschke factors? These Blaschke factors are the following. They're B, I've already used A and B, so I need a different letter over here. I'll say B gamma of Z is just Z minus gamma over 1 minus gamma bar Z, where gamma is a point inside the unit circle, right? So here gamma is just a point in the unit disk. And what are the key properties of these Blaschke factors? We've seen them before, right? We've proven those are all the conformal automorphisms of the disk up to a rotation, right? Now, I know that if I plug in a point e to the I theta, I know that modulus, one key thing over here is that B gamma e to the I theta for any theta is equal to 1. It's a unimodular function on the unit circle. So it's unimodular on the unit circle, T for the unit circle. Okay, that's an important feature because if I apply a Blaschke factor to this, what's going to happen? If I apply a Blaschke factor to the unit circle, the unit circle is going to stay put. So that says that the Blaschke factor B gamma leaves the unit circle invariant. Okay, excellent. And since it's a linear fractional transformation, therefore it's going to take this circle, which does not go through the origin. The circle does not hit the origin, so it's not going to map to a line. So B gamma maps the circle to another circle. Great. That tells us that this one is a good choice to try to solve this problem. What I'm going to do now is I'm going to specify that gamma is real. So I want gamma to be a real number. Okay. And that means that gamma is going to interchange the origin with what? Gamma, wherever gamma happens to be, and the origin are going to flip spots, right? So gamma and the origin are going to flip spots. B gamma of 0 up to the negative sign, right? B gamma of 0 is clearly negative gamma, right? So typically I'll put the gamma first. I just have to rotate this Blasky product. And then if I plug in gamma to this, I go to the origin, right? So I'm changing negative gamma on the origin. Okay, good. All right. So now what do I want to do? I would like gamma to be real, and we also want what? We also would like it to be the case that B gamma of A is the same as negative B gamma of B, right? In other words, it'd be symmetric, right? So it'd be symmetric about the origin, so that would move the circle to something symmetric around the origin and give me my annulus. Can we solve this? So this is possible. Let's check. What would that say? That would say I need A minus gamma over 1 minus gamma bar A is equal to what? Is equal to negative B, so that's going to be a gamma minus B over 1 minus gamma bar B. But remember, I don't need the bars, right? Because gamma is, I'm assuming that gamma is a real number. So we don't need the bars over here. So this says that A minus gamma times 1 minus gamma B is equal to 1 minus gamma A, gamma minus B, okay? So let's solve this equation over here. And so what's going to happen? So over here we're going to have an A minus gamma from this. Then I'm going to have a negative gamma AB. Then I'm going to have a gamma squared B plus gamma squared B. The other side of the equation is going to be a gamma minus B, and then a what? And then a negative gamma squared A, and then a positive gamma AB plus gamma AB. And this implies what? This will imply that if I put everything, I'll have an A plus B, and then I'll have a plus gamma squared A plus B, and then I'll have a what? And then I'll have a minus 2, what? The gamma will have a 2 with a negative sign, so a 1. And then if I pull out I'll have a negative A plus B, so I'll have plus A plus B, gamma equals 0, right? Dividing by A plus B, I get what equation? I get gamma squared plus, just kidding, minus 2, and then I'm going to have a 1 plus AB over A plus B, gamma, and then a what? And then A plus 1 is equal to 0, right? So I'm going to get two roots from this, right? Where are the two solutions to this? So I'll have gamma plus minus is going to be negative B, right? So it's going to be that whole mess. So it's going to be a 2, 1 plus AB over A plus B, plus minus the square root of that thing squared, right? So that's going to be a 4. 1 plus AB over A plus B, quantity squared, minus 4, that's good, all over 2, right? So that's all over 2, but the 2's are going to cancel the 4's and the 2, right? So gamma plus minus is going to be this number over here, 1 plus AB over A plus B, then plus minus the square root. Okay. Now, what can I say? One thing to observe about this is it's certainly true that if I look at 1 minus B is bigger than or equal to A 1 minus B, right? Because A is a contract, because A and B are less than 1 in modulus, right? And so what does this tell me over here? This tells me that 1 plus AB is bigger than or equal to A plus B. If A and B are what? If A and B, so this trivial inequality over here proves that fact, right? Excellent. Okay, and so now what? If they're modulus 1, this is true, right? Okay, and so now, what am I going to do? Now, that proves that this quantity over here is bigger than or equal to 1, right? Which means if I do this plus this, that'll be bigger than 1 in absolute value. So the gamma plus is bigger than 1. So gamma plus in modulus, gamma plus is bigger than 1, and gamma 1, then therefore gamma minus has to be less than 1, right? Why is that? Because I know that these two numbers, when I multiply gamma 1 and gamma plus and gamma minus, they have to give me what? The product of the roots of this equation are 1. That's gamma 1, that is gamma plus, gamma minus, right, by the the Vieti formulas, right? So these two things have to multiply to be 1, and gamma 1 is definitely bigger than 1 by this inequality over here. Therefore, gamma minus has to be less than 1, and that's what we want from a Blaschke product, right? So the solution to our problem, so the conformal mapping over here, W that we want is just going to be B of gamma minus of Z, which is going to be Z minus gamma minus over 1 minus gamma minus Z, is the conformal mapping, which is going to take this region over here and map it onto a what? An annulus that is now symmetric over the origin, so it will map onto an annulus. So this is called circle centering. It's a very useful conformal mapping trick for qualifying. Not circle-centered, circle-centering, right? Circle centering. Okay. Very useful tool on complex analysis qualifying exams, right? It's one of the multitude of things that you need to figure out how to do, right? And furthermore, this is really useful because I know exactly how to solve the Dirichlet problem for the Laplace equation on an annulus that's centered at the origin. That's easy to do, right? This allows me to offset that by composing with the Blaschke factor, right? Very, very cool. So by simply composing the Blaschke factor, I'm able to solve the Dirichlet problem on the annulus by translating it to the Dirichlet problem on this region by translating it to the Dirichlet problem in annulus. Very cool, very useful stuff. We'll see that in further videos. Thank you very much.